One of the most extraordinary moments in human history occurred when astronauts first set foot on the moon. And yet, on the surface of our own planet, there lie tracts of territory where no one has ever walked. Only a very small group of people has even glimpsed this place firsthand.
5, 4, 3, 2, 1, go!
It's not too surprising that humans have not actually walked on the floor of the deep ocean when we consider the extreme conditions that exist in that environment. Here on the Earth's surface, we live in sunlight and warmth, but the deep sea floor is in absolute darkness, with temperatures close to freezing. A person standing on the floor of the open ocean would also be exposed to the tremendous weight of the overlying water. This column of water, which is over 3.5 kilometers high, exerts a pressure hundreds of times greater than atmospheric pressure here on Earth. A person my size, for example, would be exposed to a total force of about 9 million kilograms. That's about 100 times the weight of this entire ship. A force like that would instantly crush my body to a lump about the size of a soccer ball. But the fact that scientists don't actually walk on the floor of the deep ocean doesn't mean we know nothing about it. Using research submersibles, which are specially designed to withstand the tremendous pressures, scientists have examined portions of the deep ocean floor in person by peering through windows 1/2 meter in thickness. Each window is made of a single flawless quartz crystal and is mounted in a titanium metal pressure hull 1 meter thick. But most of what we know about this remote and alien environment has not been learned by personal observation. It's been obtained by using indirect techniques. The high technology of seafloor exploration has produced a wide variety of remote sampling tools and marine robots that act as the eyes and the ears and the hands of the scientists who study the deep ocean floor. Studying the ocean floor using these remote techniques has produced a vast wealth of information. And the more we learn about it, the more intriguing it seems. In fact, the deep sea floor has not only played a prominent role in the evolution of our planet, it remains the most tectonically vigorous region on Earth.
We call our world planet Earth. A more apt name might be planet Ocean, since the oceans cover more than 70% of the globe's surface. This vast amount of water probably grew from the condensation of volcanic steam and from the melting of ice in comets which struck the primeval Earth. From the beginning, the oceans have contained more than just water. Carbon dioxide, chlorine, and sulfur dioxide, which are volcanic gases, dissolve easily in water. Sodium, magnesium, and many other elements weathered from rocks on land continuously pour into the sea from the mouths of rivers. These chemicals make oceans salty. If the surface of Earth were completely level, an ocean would cover the entire planet. But the surface is made up of two contrasting materials. Light granitic rock floats high, forming the world's continents. The heavier basaltic rock tends to sink, forming the world's deep ocean basins. The oceans average between 3 and 4 kilometers deep. However, compared to the total diameter of Earth, the oceans are but a patchy film of liquid covering the surface. Scientists have identified several different regions of the seafloor. Most of us have had first-hand experience with the shallowest and most accessible area, the continental shelf. Every time we go wading in the ocean, we're walking at the landward edge of a continental shelf. Shelves cover 1/6 of Earth's surface, sloping gently down from shorelines at an angle of about 1/10 of a degree. Worldwide, shelves average 70 kilometers in width, but in some regions, notably the Pacific coast, shelves can be as narrow as 2 kilometers.
If we started at the beach and went towards the deep ocean, we'd see first the continental shelf, and then usually there's a quite distinct break in slope, and it's suddenly steep. That's really the geologic edge of the continent. And so it's shallow at about 200 meters depth, though it varies from place to place. Suddenly it's steep, and then it drops all the way to 4 or 6 kilometers depth to the deep ocean. So it's a very tall scarp from the edge of the continental shelf to the deep ocean. That's called the continental slope. Then when you get to the base of the slope, there's a huge, long, shallow slope where all the debris that's coming off the continent is deposited. And so it's a very gradual slope. That's called the continental rise. If you're coming towards the continent, you'd slowly rise up it. And it's all the debris that's coming out of all the rivers and off of the slope by a lot of different processes all end up in a big pile, slowly getting thinner and finer as you go away from the base of the slope.
In many places, the continental shelves and slopes are furrowed by deep V-shaped valleys known as submarine canyons. Where the shelf is wide, as on the Atlantic coast of the United States, these canyons begin far out from shore near the outer edge of the shelf. On the narrow continental shelves of the Pacific coast, the heads of some canyons lie close to the surf zone.
They've been a mystery for a long time, why they're there and how they're cut so deep. And they're also very interesting because an awful lot of the sediment that comes off the continent and onto the ocean floor goes down those canyons and debauches onto the ocean floor, makes huge fans of sediment at the foot of the slope.
Beyond the continental rise lies what is quite literally the flattest region on Earth, the abyssal plain. This landscape is formed as layer upon layer of sediment settles on the ocean floor. This material, known as pelagic sediment, consists of organic as well as inorganic matter. Pelagic sedimentation is not restricted to the abyssal plain, but occurs throughout the oceans.
The pelagic sediments are made of the debris that falls out of the water column and it's like a snowfall that falls on top of all the topography. And they're made of the microscopic shells of organisms that are in the plankton, and also all the clay and dust that blows out to sea in the air and then falls down through or that is stirred up in the water. These sediments come down very gently and drape over the topography, so it saves all the mountains and hill structure, even though it softens them up, just like a snowfall would.
Farther out along the abyssal plain, the seafloor bedrock becomes shallower, and the sedimentary cover becomes thinner, exposing lava hills, which are actually the tops of volcanoes. Thousands of these volcanoes are scattered across the deep ocean floor. The larger ones are called seamounts. In fact, underneath the veneer of sedimentary deposits, the entire surface of the sea floor is volcanic in origin, although few signs of any recent eruptions are visible, except at mid-ocean ridges. Ridges are broad, mountainous features rising some 2 kilometers high above the surrounding sea floor and stretching up to 1,500 kilometers wide. The ridges are connected in a single system, snaking across an undersea landscape from one ocean to another, winding around the globe like the seam on a baseball. Unlike the crest of a continental mountain belt, which usually consists of a series of tall peaks, the crest of a mid-ocean ridge is occupied by a cliff-rimmed valley extending along much of its length. The walls and floor of this valley are split by numerous fissures. It is in this fissured valley that the most frequent volcanic action occurs on the ocean floor in the form of undersea lava flows. This volcanic activity is the key to a phenomenon that long puzzled geologists. There is a great disparity between the age of the continental crust and that of the oceanic crust. The rock underlying the continents is as much as 4 billion years old, and yet the oldest rock found beneath the ocean dates back only about 200 million years.
The fact that there is no ocean crust on Earth older than 200 million years raises an intriguing question. Does this mean that oceans didn't exist on Earth during the preceding 4.4 billion years of Earth history? Clearly, this can't be true. Fossils of organisms that lived in the sea are found in rocks older than 200 million years on every continent on Earth. In fact, fossils of multicellular marine animals range in age back at least 670 million years. And evidence of colonial marine algae, called stromatolites, have been found in the oldest sedimentary rocks on Earth. Discovered in northwest Australia, these sedimentary rocks and the stromatolites they contain are definitely of marine origin and range in age between 2.8 and 3.5 billion years. If, then, oceans did exist throughout most of Earth history, what has happened to all of the old ocean crust?
Analysis of cores taken from submarine rock reveals that the seabed becomes steadily older with increasing distance from the mid-ocean ridges. This research indicates that the sea floor originates and grows outward from the ridges. Geologists call this process sea floor spreading. The fissures atop a mid-ocean ridge are conduits through which fresh lava emerges. The lava hardens, but soon the crust is pulled open, forming new fissures and allowing more lava to emerge. Repeated continuously over millions of years, this process forms new seafloor. As the seafloor is pulled away from the ridge, it becomes cooler and denser. Eventually, it becomes so cold and dense, it can sink back into the mantle against the edge of a nearby continent or smaller ocean basin. This sinking of oceanic crust, called subduction, explains the absence of very ancient sea floor. Quite simply, it disappears back into the earth. Subduction begins at enormous underwater trenches, some of them several times deeper than the Grand Canyon. Because of the great depth, marine geologists have had to come up with a host of ingenious ways of exploring the deep sea floor.
The primary tool used by Earth scientists to study the ocean floor is a research vessel like this one, outfitted with a variety of oceanographic sampling instruments. Mounted on the stern of the vessel is this A-frame, which is a hydraulically movable rack used to lift and deploy the instruments. The oceanographic sampling instruments are tethered to the vessel with this steel cable wound around a revolving drum. Scientists can take a bite of sediment or rock from the ocean bottom using a sampling instrument like this camel grab. It takes sediment samples very quickly, but only of the upper few centimeters of ocean bottom. Oftentimes, an undisturbed sample of the deeper layers is required to examine variations in the accumulated sediment on the ocean bottom with time. This box corer takes an entire column of sediment, which later can be split open, and the individual layers analyzed like pages in a book. But marine geologists need more than physical samples to understand the sea floor. It's like trying to understand an entire city by only visiting certain buildings and street corners. By examining the shape and global distribution of submarine landforms and determining their rock composition as well, geologists have been able to link the processes which create these landforms with the formation of the ocean crust itself. Most topographic mapping techniques used in seafloor exploration are based on the principle of sound waves bounced off the sea bottom, a technique called echo sounding. First developed for the military detection of enemy submarines in the 1920s, echo sounding devices emit a pulse of sound toward the ocean bottom and record the amount of time it takes for that sound to bounce off the bottom and back to the device. By converting echo time into water depth, an echo sounding device draws a two-dimensional profile of the ocean floor beneath the research vessel. In recent years, however, marine geologists have employed more sophisticated acoustical techniques to map the topography of the sea floor. These robotically controlled imaging devices can map an area of the ocean floor tens of kilometers wide in a single pass. This three-dimensional view of the ocean bottom can be clearer, more detailed, and even more valuable than the view of the ocean floor from the window of a research submersible.
One such imaging device is currently being used to map the territorial waters of the United States. In 1983, the federal government expanded this region to include all terrain within 200 miles of American shores. The U.S. Geological Survey was assigned the task